welcome back. In this video, we're going to talk about a couple of additional discrete distributions, namely the hypergeometric and the negative binomial distribution. In our last video, we were talking about the binomial distribution and identified some properties. So in this one, we'll kind of build off of those because they both have some binomial similarities, especially the negative, the one that we're getting ready to talk about. All right, so first one we're going to do will be the negative binomial distribution. Okay, what this one does is this one adds an extra requirement to the binomial distribution. Okay, if you recall from our binomial experiment, we defined that we needed a predetermined number of trials, we needed a constant probability on each one, and then each event had to be able to be defined as a yes, no, true, false, a, not a type of problem. So all of those are still valid for this. Okay. The extra stipulation that we're adding now is that the random variable x is going to be defined as the number of failures before r successes. Okay, so here's our random variable. We're going to declare it as a negative binomial. There's the NB, and then the functional parameters that we're going to pass in will be the number we're looking for, the number of successes, and then the probability of failure of an attempt. Okay, so again, we kind of define our parameters. R is the number of successes that we're looking for. X is the number of failed attempts. Wow, if I could learn to spell, that would be great. Okay, of failed attempts, and P is the probability of failure on a given attempt. All right, so just like before, probability of X equals X is negative binomial XRP. And so our equation looks something like the following. The combination term in front of this becomes X plus R minus 1, okay, and then R minus 1 is the number of ways in which that's going to happen. So we're going to take the probability of a failure, which would be an R to our R, and then 1 minus probability P raised to the X, where X is equal to 0, 1, and 2. Okay, if we do that, okay, we can show that the expected value of this distribution is R times 1 minus P over P, and the variance of our random variable is R times 1 minus P over P squared, okay? What this problem allows us to solve is the until scenario. Okay, before we couldn't do that. So now we're looking at examining the number of attempts that something will happen until we get the specific number of outcomes that we want. Okay, sometimes you'll see this written, any problem that has a before written in it, that will be kind of a tip off that this is a negative binomial. Now, it's kind of this form of it isn't quite as clear as, say, maybe a slightly different form where maybe I want to know the number of trials that I have to do before I have R successes, okay? In this case, I'm going to define a new random variable y being the number of trials. So if that's the case, then y is simply x plus r, okay? And so in our equation up here, we can kind of look for x plus r, and you see it shows up here that now becomes my random variable of y instead, okay? And so that's probably a better form of it. So we're looking for the probability that y is some numerical value, and then we're going to take that on y minus 1 to r minus 1, and then probability p raised to the r power, and then 1 minus p raised to the y minus r power, where y is the values of r plus 1, so forth and so on. If we do that, the expected value of y is simply r over p, and the variance of y is r times 1 minus p over p squared. Okay, now, if you look at this, this looks exactly like the binomial distribution equation that we talked about in our last video, okay? But you'll notice the one difference that we have is a minus 1 slapped on the end of this thing, okay? And the way that you can remember this is because you're doing an until problem, okay? And the until problem mandates that I have to have a successful attempt as the last one in the chain. Okay, so imagine that I have a sequence of events of looking for 2 successes, that it takes me 6 tries to find my second success. Okay, and so if I do that, that means that if the last one has to be a success, then the first 5 are now F, S, F, F, F. Could be one of the patterns in any of the combinations that we're looking for. So we're really only looking at that combination here, all right? Okay, and the number of ways that I can get basically 1 success in 5 attempts. Okay, and that's what this is doing. Okay, this is the combination that participates on that first string, because this doesn't matter. The last one is a guaranteed success to meet the criteria of our problem. Okay, so it is a binomial, but we're just basically subtracting 1 off of it when we try to do that. So let's give one a shot and see what we can do. Okay, so we've got an example. We have a medical study in which a doctor wishes to recruit 5 patients to participate in a study. we're going to define the probability that a randomly selected patient agrees to participate as being 0.2. Okay, we want to find the probability that it takes 15 patients must be asked before 5 are found who will participate. Okay, so this is 15. This guy here is our number of trials. Okay, so we're going to use the second formulation for the negative binomial on this one. Okay, so we're going to require the random variable x is the number of failures before 5 successes. And so if we do that, we calculate this quantity as then being 15 minus 5 is equal to 10. Okay, and so we're looking for the probability of x equals 10 on a negative binomial. Now again, we had the keyword before here, okay, or until 5 are found. Okay, that's the tip-off that this is a negative binomial as we start to kind of look at it. So if I do this, it's a negative binomial, my x parameter is 10, my number of successes I'm looking for is 5, and then the probability of achieving a success is taken as 0.2. So if I plug in my equation, it becomes 10 plus 5 minus 1, and then 5 minus 1. So it's this plus this minus 1, and then this minus 1 in the bottom. It's the combination of those number of ways. And then I have 0.2 is the probability that they accept. So that's the 0.2 raised to that number of successes. And then I need a complement of that, 1 minus 0.2, which will be 0.8 obviously, raised to the rest of them, which would be 15 minus 5. Okay, and so if I do the math, this is 14 on 4, 0.2 raised to the 5th, 0.8 raised to the 10th is a probability of 0.034. All right, so this is the scenario that we can work with for a negative binomial. So the probability that it takes me 15 before I find 5 of them is a little more than 3.4%. Okay, and so you can repeat this process for, x equals 1, x equals 7, x equals 9, so forth and so on. Well, actually, this is going to be a 0 probability because I can't have 5 successes on one trial, but I can go all the way up to, any number of these things happening as we start to continue on. So that's the game that we can kind of play with the negative binomial. So it's not hard, just you got to kind of keep track of the terms, and you got to remember that minus 1 that's hanging out here. All right. Okay. Our next method then that we're looking at is called the hypergeometric. Okay, and you've seen this one. Okay, when we started doing some of our counting problems, we talked about pool problems, and a pool problem is nothing more than a hypergeometric. Okay, and I'll show you how we come up with that here in just a second. So the requirements is that we're going to define a random variable x as being the number of successes in a sample of size n. And then we're going to define another random variable that we're going to call as capital M as being the number of successes in the entire population, capital N. So notice lowercase, uppercase, uppercase. Okay, so these uppercase guys are working on the entire population, and then N has to do with my sample, and X is the number of the events in the sample that I'm looking for. Okay, so we're hypergeometrically distributed if we have a probability of X equal to my little x, being hypergeometrically distributed. The parameters I need are x, little n, big M, and big N. Okay, and if I do that, then this becomes just a product of combinations, if you will. I'm looking for the number of ways in the sample that I'm looking for out of the total number possible. Okay, and then I'm taking what's left over, n minus m, and I'm taking the leftover amounts out of the tries that we have. So this is n minus x on this one, all divided by then my number of attempts out of my total number of possible events. Okay, this is nothing more than the problem that we did before with NA over NS, which was our pool problem. Okay, now there are some limits on x because mathematically I can get into some trouble with negative values. I am bounded on the lower edge by a 0 value. So if for some reason this term comes out negative, you would use 0 as the lower bound limit on x, and then the minimum would then be either n or m. Okay, so depending on how we start to do this, we've got to be kind of careful on our limits. So that's the one little change that goes in on the hypergeometric. I'll show you here an example here that we're getting ready to work. Okay, so let's take our aces problem. Okay, so let's define x is the number of aces when we're drawing 10 cards out of a standard deck. Okay, so the variables that we have is n is equal to 10, because that's the number of cards that I'm pulling in the sample, 10. Okay, capital N, assuming that it's a fair deck, is 52 cards. And then M is the number of successes that are possible in the population N. Okay, and so for a standard deck, we know that we have 4 aces. That's why we have M equal to 4. And if I do my limits on this, my limits of values of x are going to be 0 less than or equal to x less than 4. All right, because this one we have 10 minus 52 plus n. This would be a negative number if I plugged in my n, m, and capital N on that. So that's why we lower bounded at 0, and then my minimum is either 10 or 4. So then the 4 controls. That's where this piece of the puzzle comes from. So that's my entire distribution for this math equation is valid only on those limits on x. All right, so let's just assume that we want to find the probability that I get 0 aces, okay, when I draw 10 cards out of a deck. Okay, so this is a negative binomial. Okay, we're looking for the number 0. We have 10 trials. We have 4 possible successes and a pool of 52. Okay, and again, limits are 0 less than x less than 4. Okay, if I plug into my formula on this, we're looking at 0 out of 4. I'm looking at 52 minus 4 and 10 minus 0. And then I'm dividing that all by the combination of 52 divided by 10. And that number would be 0.413. Now, this is a pool problem as we defined it. If you remember, I showed you how to draw these last time. If this is my sample space that was 52, we're pulling 10 as the total number of ways to pull 10 cards out of 10 card hands out of 52 possible cards. Okay, I then have an event A, which is my number of aces, which is 4. So that's my capital M. Okay, and then this guy then is n minus m, 48, 52 minus 48, right? Because we had 52 here, so that's n, you can see. And so now the event that I'm looking for in this scenario is I want to pull 0 out of this, which means I have to pull 10 out of this. Okay, and when we do that, that's the exact way that we calculated the probability in that. Here's the first event, so that's my ace event. This is my not ace event. I'm multiplying by that, and then this is the number of ways of the sample space. It's as simple as that, okay? So it's kind of a binomial thing because it's one of two outcomes, but the hypergeometric allows us to solve these pool problems, numerically. Now again, typically I like to draw the picture just so I can keep my terms straight, but it's pretty convenient on the way that we can do that, but I have to be able to cast a problem into an event and then its complement. You have to be able to cast this. So that condensation technique we did with like the light bulb problem, I would have to do a little bit of modification to the problem to come up with a scenario that looks like this. And then you're off to the races being able to figure out probability for a certain event. Now, what I've done in this is that, repeating for the probability distribution that our x is going to be any of the values of 0, 1, 2, 3, or 4. That defines my entire possible range of values because obviously you can't have more. Okay, the probability of x then for this, my first value we did was 0.413, and then I can do the math similarly to find all the other values, and that's what I've shown here. So if you were to kind of graph this distribution, you would get something that looks kind of like this, that it kind of peaks somewhere between 0 and 1, and then it drastically falls off for 2, 3, and 4. Okay, now, the other definition that we need for this is we need to be able to come up with expected value in our variance for this particular distribution. So we're going to define the probability of success as being the number of possible successes in my total pool size. Okay, so if we define that as m over n on this, then for a random variable x that is hypergeometrically distributed with the same parameters, the expected value of x on this is just simply n times p. Okay, or this becomes n times m divided by n. That's the hypergeometric definition. And then the variance of x then is n minus m divided by n minus 1, capital N's obviously, and then multiplied by n times p, multiplied by 1 minus p, which is the complement of that probability. That's how you get the variance. All right, so for our previous example where we're pulling aces out of a deck, our probability of success is going to be on the, and what this is kind of a correction for that first pull, that we're going to have 4 chances of a success on 52 is going to be our desired probability for this calculation. The expected value of this variable then is n times p, which is n times n divided by n, capitals again. So if I do the math, 10 times 4 over 52 gets me an expected value of 0.769. So the expected value of the number of aces that you would pull is somewhere between 0 and 1, okay, on 10 cards. Okay, the variance of this then, if I plug in the math to our equation, you can see that we're doing 52 minus 4 and 10 minus 1. Okay, and then I'm doing 10 times 4 over 52. So again, this term is n times p. This guy is 1 minus p. Okay, and then our math becomes 0.585. And with this, I could go easily and do the standard deviation of my random variable x would be that guy, whatever the math ends up showing. Okay, so that's all there is to doing these. So it is a pool problem kind of setup. But what's cool is now you have a predictive model for expected values of your random variable that you're looking for. Okay, but at the heart of it, the probabilities are calculated in exactly the way that we did those pool problems, that light bulb problem back in the day. So anyway, I know this one's fairly short. It's a couple of real quick distributions. Both have their uses. Both are kind of variations on binomial, but for what they are, they're pretty handy. So that's why I wanted to kind of at least talk about these two different ones. Okay, so again, if you've got any questions on anything, toss us a comment down below. As always, like and subscribe to the videos, and let us know what we can do a little bit differently. Otherwise, have a great afternoon and happy engineering.